So with conservation laws, the basic idea is that the amount of stuff at a particular location changes by what's coming into the region, by what's going out of the region, and the addition of whatever might be created or destroyed, in the case of a negative term, at that particular place. So if we let U denote the density of whatever stuff we're interested in, and so this could be heat, number of cars, biological species, chemical species, whatever. It's just the density of stuff. Then we'll let phi be the outward flux of stuff. In one dimension, this will be moving from left to right. And then F will be the rate of creation or loss of stuff at a particular location. So this would represent sources or sinks. So now if I've doodled a little picture sort of what's going on here facetiously, as if X were a little box on the real line. So maybe U represents the amount of stuff that we've got in this box, how full it is. Then phi is the phi slightly to the left is the amount coming in from the left, and phi slightly to the right is the amount leaving at the right. And the total amount of change in this region is just going to be the incoming minus the outgoing. So if our domain omega is a one-dimensional region, then if we have any small interval from A to B, then what we see is that the total amount of energy of stuff U in the region, well, you always find the total amount of a thing by integrating the density of that thing, and we're integrating over the interval, so it's a space integral dx. And then we're looking at the rate of change of the total amount of stuff. And so this is going to be the amount that comes in at A minus the amount that comes out at B. And recall, phi is a vector, and so it's the flux from left to right. And then we must also add in whatever is coming in at locations inside the interval. So we have this set up right here, and assuming that U is sufficiently smooth, we can bring this this derivative inside, and then becomes the integral from A to B partial of U with respect to t. And on the right hand side, I can rewrite this portion right here in terms of the antiderivative with respect to space, which would be phi x evaluated from top to bottom times dx, plus then this integral of sources and sinks. And then collecting all this under one integral sign, I have ut minus phi x. There should be a minus sign in front of that integral because the orientation is reversed. Sorry about that. I forgot my fundamental theorem of calculus. So then that makes this a plus, and then I have minus f all inside the integral. And now here's the interesting thing, is that this is true for any little interval inside the domain. That means that this integrand here has to be identically equal to 0. The reason why is because it's a continuous function, and so if there were any place where, say, it were like strictly positive like that, then we could choose our AB to be this little interval right here, and then we would have a strictly positive integrand over some little interval. We would end up with a strictly positive integral, and it would break this identity right here. So we can conclude then that it has to be the case that ut plus phi x is equal to f. And so this is our main conservation law.